In this video, I want to talk a little bit about how carbon dioxide is carried within the bloodstream. And it's carried in both the venous and the arterial circuits. Certainly, carbon dioxide is produced as a waste product in our systemic tissues, and so systemic venous blood will have a larger CO2 content than the arterial content. But either way, we're going to carry it in the same three mechanisms. The first one is as the dissolved gas. Carbon dioxide as a dissolved gas is carried at about a rate of 5 to 10% of the total. This is actually much higher than that for oxygen. If you recall, oxygen was carried 98+% bound to hemoglobin. Only about 1.5% was carried in the dissolved form. This is explained by the much lower solubility of oxygen in aqueous solutions compared to CO2. Well, that still isn't carrying most of our carbon dioxide, however. So we also carry carbon dioxide bound to hemoglobin. So as our tissues produce carbon dioxide through aerobic respiration, essentially by Krebs cycle reactions, that carbon dioxide will diffuse out of those cells and bind to hemoglobin in the bloodstream and form what's known as carbaminohemoglobin, the second term. That actually accounts for 10 to 20% of the carried carbon dioxide. This is still not a significant fraction. We need to come up with what's our third and most important method of carrying carbon dioxide. One important side effect of this binding to hemoglobin, however, is that it enhances the unloading of oxygen from that hemoglobin, delivering more oxygen to the tissues as that hemoglobin passes through the systemic capillaries. Now, in those systemic capillaries, our carbon dioxide level is rising. The CO2 produced by the cells is diffusing outward and into the bloodstream, and inside red blood cells, it will react with water, catalyzed by an enzyme called carbonic anhydrase, to form carbonic acid. This then rapidly dissociates into a bicarbonate ion and a free proton. So here is our most important third mechanism of carrying CO2, actually within this free bicarbonate ion. Now, what we want to do is strand it as that ion, because you can imagine as this reaction is right shifted, as the CO2 is produced and reacting with water, the metabolites over here on this side going to accumulate. Well, they could re-react and drive it backwards, and we don't want that to happen. And so what we do is the free protons end up getting buffered by binding to hemoglobin. This actually further enhances the unloading of oxygen into this tissue. A side effect, though, of that is known as the Haldane effect. The fact that we have stabilized this free proton by binding it to hemoglobin strands, effectively, the bicarbonate ion by itself, right? And we can carry our carbon dioxide out of the tissue as this free bicarbonate ion. When we reach the lungs, what happens is the carbon dioxide is going to diffuse out of the bloodstream and is going to decrease there. And that's going to cause this carbonic acid equation to shift leftward, right? We're going to now have the bicarbonate begin to recombine with the free protons to form our CO2, the volatile gas that can move into the alveolar air for removal from the body. This free proton is coming off the hemoglobin, enhancing its affinity for oxygen, entirely adaptive to what we need to have happen at that lung surface. This reversal of the carbonic acid equation is absolutely essential, as we cannot exhale the free bicarbonate ion. It has greater solubility than CO2. We carry our CO2 as this bicarbonate ion, but we need to reconvert it back into CO2 through the law of mass action. Remove the CO2 by diffusing into the alveolar air, drive the reaction leftward, and get our CO2 out of this soluble bicarbonate ion into a form that can be removed from the body.